to Unit 3, Lesson 8. As usual, you're looking for the tasks to complete for U3L8. You can find it under assignments or on the weekly calendar. Today's date is the 7th of December. Our goal today is to start talking about gas properties and introduce you to the gas laws and a little bit of math. We've successfully stayed away from math for this in this course, but now we're going to have to veer into it just a little bit. I'm not going to hit you over the head with anything too complicated. So we'll start off with the usual chat room share. The question for today is this. What's your favorite place you've ever visited? With lockdowns and everything, traveling is not going to be something you should do in the near future. So let's think back on memories of places we've been to before and what you want to share. So again, what's your favorite place you've ever visited? You guys haven't answered this one before yet, have you? No? Okay. Think about that for 20 seconds. And don't forget to say hi and check in with the person you're in the room with too. We'll come back together in 2 minutes. Rooms are open. Thanks for sharing, everybody. Next on the list is just a quick check of the homework assignments. Again, we had the classwork that you needed to wrap up. That is looking good on Canvas from what I can see. I'm seeing 13 attempts on here. And then you had the Ed puzzle for homework, which was just kind of a little review of Boyle's Law on gases. So if you haven't had a chance to do that, remember there's an alternative Google form that you can also complete. I'll be checking that. Looks like a few people actually did do the Google form as well. Any questions on that stuff, the homework? Anything you got stuck on? All right. I wanted to show you one last cool thing with phase changes. And it's going to include 2 different kind of short Ed puzzles and a little demo video that I'm going to show for you right now. So you've got 2 options here where you can either try this activity. It's a Flipgrid activity, but it is optional because it is a little dangerous. But either way, you'll be working through this quiz on Canvas. So on the tasks to complete list, I am now on step number 3, atmospheric pressure can crush. You can watch the atmosphere crush a can. I'm going to show you the demo video. We'll just watch this together right now. Make sure my screen's optimized. Okay, check it out.
Hi, Science 2 kiddos. Going to use this video as a demonstration of what's called the atmospheric pressure can crush. Now, you can either just watch this video, or an optional alternative is you can try this at home. However, you do not have to. This is a little bit dangerous, but I'll walk you through what you need. Safety is going to be the most important thing, so you need some kind of eye protection, glasses or sunglasses. I've got my lab coat on, and something to protect your hands. You're working with boiling water. That's the main thing that's dangerous, as well as a hot surface, so oven mitts or something are good too. Let's do some science. Now, what you're going to need if you do try this at home is an empty aluminum can, as I mentioned with the homework. You'll need a bowl with some water in it, just regular sink water, and it doesn't have to be glass. Glass just makes things more visible. And so you're going to fill the glass bowl with water from the sink. You need to fill the can about 1/4 full of water. You really don't need that much. I mean, I would use about this much or so and just pour it on in there, like so. And you're going to need tongs to grab this can, because what you're going to be doing, as you can see over here, is heating the water in the can on a stove top. And you'll want to keep it going until you hear that. I'm not sure if it's coming through in the video, but you can kind of hear it bubbling in there. And there's a, you can see the water vapor coming out of the opening on the top here. So then what you're going to want to do is use tongs, again, because you're going to grab the edge of the can here, like so. And what you're going to do is you're going to invert it upside down into the water. So you want the opening on the top to go into the water. Okay, so that's what I'm going to do. Again, be very careful if you're trying this at home. You don't have to do this at home. You can just watch this video to answer the questions, but if you want to give it a try, have some adult supervision, someone to help you, and just make sure you're being safe. Keep your distance. So watch what happens when I now take this can that has boiling water in it and place it in the water. Here we go. Now, you'll notice the can imploded, and that wasn't me squishing it with the tongs. That was something else going on there. And so the question you'll need to answer as part of the Canvas quiz you're working on is why that happens. So again, please answer the questions in the quiz. If you're going to try this at home, please be safe.
All right. So, show of hands, real quick. How many people had seen that before? A can being crushed with boiling water in it. No? Now, again, I want to emphasize that wasn't me with the tongs. That was just something that happened. And you can make that even happen to something like a huge barrel, which you'll watch an Edpuzzle video about. So, as I was saying, you just now need to work on that quiz titled Atmosphere Pressure Can Crush Quiz. If you want, again, it's optional. You can go ahead and do the Flipgrid activity and try this actually at home if you have an empty can and can boil some water. Just be safe about it. But you can post a video right there with Flipgrid, but you don't have to do that. What you do have to do is then answer the questions. And so the first one's a little prediction, like why do you think it happened? Again, no right or wrong answers here, just take your best guess. And then there's gonna be 2 Edpuzzles, so make sure that you complete the one that's appropriate for your class. This is Science2B. So click on Science2B Edpuzzle, you're gonna watch a little video about Can Crush there. And then just in this text box here, just type done. Once you've completed the Edpuzzle, all you have to type in here is done. And then step 3 is gonna be a little bit of a putting steps in order. Question 4 is another short Edpuzzle. Again, make sure you're watching Science2B. This is the second Edpuzzle. And then I believe that's it. Just type done for that quiz. So I'm gonna time for 15 minutes to let you work through this. But once it looks like everyone has it done, we'll come back together. I'll be here listening if you have questions, if you're not sure what to do. And I have links to the original YouTube videos too if you can't get the Edpuzzle to work. Go for it. Let me know if you need help. Again, AirPod takes a little while to load too, so we'll have to give it a minute. It'll come up with a join code in a second. There it is. All right, so make sure you've clicked on that link I threw in the chat for Nearpod, and the join code you want to enter is A8D3U. Put the join code in the chat as well, so you can access it there. It's also always in the upper left corner. As usual with Kahoot or anything else, please use a name that is close to yours so that I know who's who. Okay. Seeing 9 people on. Should be 13 of us here, 12 of us here today. Okay. Now again, since we're doing a little math here, I'm actually going to divert and share my screen to my iPad again, but we'll come back to the Nearpod for a little question review. So I'm going to stop my share here and go to my iPad, and let's look over this stuff. All right, can I get verbal confirmation? Everyone's seeing nature of gases in front of them?
Yeah.
Yep.
All righty, let's blitz through this. We're gonna make 3 assumptions about gases. So we're gonna focus on gases in particular. You're already familiar with this from that PhET simulation that we did earlier. So you've seen, the gas particles dancing around, but we're gonna assume that gases are composed of small little particles, as pictured here, that are constantly moving and banging into each other. And if you remember that animation, right, you could literally watch them as they like dinged around all over the place. And gas particles bounce off each other and surfaces with equal energy. In other words, if you have 2 gas particles that then come together, they will smash apart and move apart with the same amount of energy. So it's not like 2 cars crashing where they're going to like merge into each other or one's going to stop. We can assume that collisions are elastic. So just motion is continuous. They're bouncing all over the place. This is what generates pressure. Anytime you put a gas in a container like this, all those collisions, when they bang against the outer edge, as you can see with those little red arrows there, that's what's creating the pressure. And that's what you feel as well as gas is pressing in on you. You can wave your hand around in the air, you can feel the air around you. That's you smashing into air molecules. So how do we measure air pressure? Some of you might have one of these outside. It's called a barometer. And that's just measuring how much, literally the atmosphere, right? How much air pressure you're experiencing in the atmosphere. And it helps you predict some things about the weather, right? According to this, apparently lower pressures, atmospheric pressures indicate wet weather on the way. Higher pressures indicate warmer weather. That's not entirely accurate all the time, as far as I know. Now, in terms of the units, this is where things get a little weird with pressure. So the units of measuring gas pressure, the most common one is the kilopascal, abbreviated as kPa. But you also see pounds per square inch, called PSI, millimeters of mercury, which I'll explain in a second, and atmospheres. So all four of those are units you could use to measure gas pressure. It's just like using liters or milliliters or kiloliters for measuring volume or something like that. And so it's important to understand the relationship between them. So here's what they're all equal to, right? One atmosphere is the same as 760 millimeters mercury, 101.3 kilopascals, and 14.7 psi. You can convert between any of these. You can jump around. They're all connected to each other. So that's not something I'll ever expect you to memorize. You'll always have that as a reference. Now, you might have noticed one of the measurements was millimeters of mercury. The symbol for mercury is Hg. And millimeters hopefully strikes you as weird because that's a measure of length, right? But it's based on this. This is one of the earliest mercury barometers. So mercury is actually a liquid metal. You can see it in there. And since it's a liquid, you can put it in a little petri dish container. And what's happening is atmospheric pressure, all the air that's on top of it pushes down on that liquid, the same way it pushes down on you. And it's going to force some of that liquid up into this test tube. And so we can then get a ruler and measure how far up the test tube it went. And that's sort of where the millimeters of mercury comes from, right? Is that if there was a lot of atmospheric pressure really weighing down, then it would push this mercury higher and higher up, right? There would be a much higher millimeters of mercury measurement. If atmospheric pressure was low, then this would drop down. So that's just the origin of that type of measurement. Okay, all of this is building up to what we call the gas laws. And this is what we're going to focus on for the remainder of our time here in December. We're going to look at the relationship with gases between pressure, temperature, and volume. These are the three we're going to focus on. Don't worry so much about moles. Moles is the amount of gas. We're going to assume that that's always constant. It's always the same. So you don't need to worry too much about that. But what happens when pressure increases? Does temperature increase? Does volume also increase? Like, what's the trend? What's the relationship between these things? So I already mentioned there's 4 different units for pressure. And so you'll see each of these and you can convert back and forth between them. We'll practice that in a second. Temperature is measured in degrees Celsius or in K. Does anyone know what K stands for?
Kelvin.
Very good. Kelvin is the SI unit for temperature. You can convert back and forth using this equation here. So if you know your degrees Celsius, all you have to do is add 273 and that gives you the Kelvin. Or vice versa, if you subtract 273 from Kelvin, that'll give you the Celsius. So the first thing you need to get comfortable with is converting between units. We call this dimensional analysis. I'm going to try to keep this simple. You're going to be using equivalent ratios to convert back and forth between things. So I'm hoping we all agree in this picture. Everyone see there's a 1 meter long ruler and there's a 100 centimeter long ruler. What do you notice about the length of 1 meter and 100 centimeters?
The same.
They are equal, even though they're different units. And so you can create what's called an equivalency. You can create a fraction where you put 1 meter on top and 100 centimeters on the bottom, or you can flip it. You could do 100 centimeters on top and 1 meter on the bottom, but that's an equivalency. We're basically saying that this is equal to that. This is a fraction that adds up to 1. And this is useful because we can then use it in conversion math. And so I'll do kind of a simple example to start. So here's another equivalency conversion ratio. Everyone knows that there's 4 quarters in $1, right? And so I know some of you can do this in your heads. So what if I had 12 quarters? Can anyone tell me how many dollars I would have if I have 12 quarters?
3.
Very good. A lot of you just do that math in your head, right? But what I want you to get used to is doing a little bit of fraction math, where instead of just doing it in your head really quickly, you got to understand that you got 12 quarters. You're going to multiply by a fraction. On the bottom of the fraction, you're always going to put the existing unit, so the unit that you are starting with. And on the top of the fraction, you always put the unit you want. So where are you going, right? I'm asking for dollars. And then that's going to give you dollars. Here's why. Does anyone know if you put quarters here on the bottom and you've got quarters technically here at the start too, at the top, does anyone know what those two units do to each other?
Cancel out.
And then we're left with dollars. So how do I know this relationship? What's the relationship between dollars and quarters? It's right here, right? I know that $1 is the same as 4 quarters. And so you're just doing 12 times 1, and then divided by 4, which gives you 3, as was shared earlier. So I know that seems like a lot of work to get the same answer, but it's going to be a little more complicated when you're suddenly using these as conversions, right? And so this is something I want you to practice. I'm going to do the first 2 as examples, and then I'll let you go to do them on your own. Let's take a look at A. I got 2.5 atmospheres, and they want to know what's the equivalent in kilopascals. So I'll start with 2.5 atmospheres, multiply by a fraction. Again, on the bottom, I'm going to want to put atmospheres because that's my existing one that I want those to cancel each other out. They want kilopascals, so I'm going to put kPa on top, and therefore I know my answer is going to be in kPa because that doesn't cancel out. And so the relationship is right here. I know that 1 atmosphere is the same as 101.3 kilopascals. So I put 1 for atmospheres, 101.3 for kilopascals. Again, I got that from here. And then you're just doing 2.5 times 101.3 divided by 1, which will be the same thing. And you end up getting something like 253.3. And so that's conversion math. I'm never going to make it any harder than that. Let's look at C next. This is a temperature conversion, 73 degrees Celsius to Kelvin. This is a lot easier. You don't actually have to do any multiplying or anything like that. Just remember that if you want Kelvin, you just take your degrees Celsius and you add 273. That's just the conversion. And again, I'll give that to you. But if you add those up, so you're just going to do 73 plus 273 gives you 346 Kelvin. All right, let's give this a try. So on Nearpod, so the little Nearpod thing you joined, you should now have a quiz that you can try. So give this a go. I'd like you to try to convert 511 millimeters of mercury into atmospheres and type your numerical answer in. See how you do. All right, good. I'm seeing answers rolling in. Anyone struggling? If anyone's having a hard time, here's the equation you want to use. You want to take your 511 millimeters of mercury, multiply it by a fraction with atmospheres on top. We know it's 1 atmosphere is the same as 760 millimeters of mercury on the bottom. Millimeters of mercury are going to cancel out. And you know you're going to get a small number because you're doing 511 times 1 and then dividing that by 760. So you're going to get 0 point something. All right, seeing answers from most people. I like that some of you are including the unit with it. That's okay, I didn't make that clear. So, interesting. What I'm curious about is, all right, if I share my screen, if you're looking at the shared screen, can you all see the answers you provided, or are you seeing something different? Are you seeing a list of answers from each person?
Yeah.
Yeah, cool. All right, looks like most people got the same number, 0.67. Looks like we're feeling good. Okay, next one is going to be a little bit easier. This is a temperature conversion. This one's multiple choice. What is 500 degrees Celsius equal to in Kelvin? I have the conversion equation for you at the top of the question. Give it a go. All right. Okay, seeing answers from just about half of you. Let's try to get a few more in. All right, I'm going to share the results. But it looks like all of you are on the right track. It is indeed A. And again, all you're doing is taking the 500 and adding 273. So really, it just comes out to 773, if I remember correctly. It's funny, it doesn't show me the full question on here. Okay, let's just keep looking at the slides through Nearpod because that's where we are right now. Here are the correct answers to each of those, so you can check yourself and redo the math later if you want. All right, so let's introduce you to your first gas law. You're gonna, homework, we'll review this a little bit and we'll continue with this in our next class meeting. Boyle's law is the first gas law, which is gonna relate pressure and volume. So what's going on with pressure of gas and volume of a gas? And I think it's not surprising that the pressure is inversely proportional to the volume. So what that means is if you have, I'm not sharing my screen. Here we go. So here's the slide we're on. Sorry about that, everybody. So Boyle's law, again, is showing you that they are inversely proportional to each other. And what that means is anytime that you've got a moment or a situation where pressure is increasing, can anyone tell me then what the volume would be doing if they're inversely proportional?
Decreasing.
It would decrease, right? And you can have the same situation vice versa. Volume increases, pressure is going to decrease. So that's just the behavior of gases. We can mathematically express it this way. P1V1 equals P2V2. So this is a little equation that we'll have you use to solve a couple problems. A couple things to note. For pressure, it can be in any of these units as long as they're matching. As long as P1 is the same as P2. So if P1's in atmospheres, then P2 needs to be in atmospheres as well. Same thing for volume. Volume can be in milliliters or liters as long as whatever unit is used on V1 is the same one that is used in V2. we're assuming that temperature is kept the same and the amount of gas is kept the same, right? So we're not adding any gas between these situations. We're also not changing the temperature at all, right? Temperature remains constant. And so here's an example of a kind of question we might throw at you to use this equation, right? So if a balloon filled with 425 liters of helium gas is kept at a pressure at 101.3 kilopascals, if the balloon floats away, reaches the high altitude, changing the pressure to 47.2 kilopascals, what would the volume of the balloon be? So I know these questions are kind of tricky, but like any math word problem, the trick is to identify your variables, right? And so here we're given 425 liters. I'm going to go ahead and label that V1. That's my first volume. That is a gas that is kept at 101.3 kilopascals. So can anyone tell me what variable is that? 101.3 kPa. What's that going to be?
Pressure.
Yep, P1, right? So we've got our V1 and our P1. Those are our initial pressure and volumes, okay? So then the balloon escapes and it floats high up into the air. Now the pressure has changed to 47.2 kPa. That's going to be my P2. So when they ask the question, what are they asking us to find? What's the one variable we don't know in this equation?
V2.
Yes, so when they ask for the volume, what they're asking for is V2. So now you just have to plug those numbers in and solve. And so if you know your algebra, all you need to do is basically bring P2 over here. You're going to rearrange the equation. So you just know that you're going to be doing P1 times V1 divided by P2, and that'll give you your V2. I have this drawn out on the next slide just to save time. So here's an example of how to solve this equation. I know typing it up looks a little weird, but basically here is all the numbers entered. This is how I like to do it, right? It's the same equation, but I've entered the 101.3, 425, 47.2, and there's our unknown V2. That's what we're trying to solve for. And again, you just divide both sides by kPa. By this one, you're going to get rid of 47.2. So I just bring it over like that, bring it under, and then you just solve for V2. And I got 912 liters. There was a practice problem I wanted to give you, but in the interest of time, we'll hold off on that. We'll get more practice with our next class meeting. But the point is, what I want you to notice is that, again, back with our original situation here, pressure is changing. So notice here was our P1, and here was our P2. And you can already make a prediction here. Can anyone tell me what happened to the pressure? Right, as we change from P1 to P2, did pressure go up or down?
Down.
Yeah, and so you would expect volume to do what? If pressure went down, then volume would go
up.
Yeah, go up. And so we know that our answer will be larger than 425 liters. 912 liters is definitely larger than 425. And so it makes sense in terms of Boyle's law as well. So again, you'll get more practice with that with the homework. There's a little Edpuzzle video you're basically going to watch, and I think I have a little kind of Canvas quiz where you can practice some math, and we'll continue with that in our next lesson. Any questions or comments on that so far? All right, kiddos, that is it for me. Thank you very much. Have a good rest of your day.
Thank you.
Thank you.